types of trees. If you take a tree data structure, there are different types of trees are actually there, and few are listed here. General trees, forest, binary trees, binary search trees, expression trees, AVL tree, B tree, like this there are multiple types of there. Many more types are also there, and only few have listed here, and let's discuss one by one in detail. The very first type is general tree. In a general tree data structure, the data elements will be stored in a hierarchical fashion. Here the top node of a tree is the root node, and each node except the root node will be having a parent. If you take any tree structure other than the root node, all other nodes will be having a parent. If you check here, this is the root node. Since it is the origin of the node, it doesn't have any parent node, and all other nodes, if you check these these four nodes are the children node or the child node, for the parent node the root node, and the parent node here is all these four nodes are a parent. And if you check this node, for this node is acting as a parent node, and for these two nodes this node is acting as a parent node. So other than the root node, all other nodes would be having a parent here. And also in general tree we can have multiple subtrees, not like only one subtree or only two subtree or only one. It can have 0 subtree or more than 2 subtrees also. It can have any number of subtrees a general tree can have. Since it has multiple subtrees, performing operations like insertion, deletion, traversal, all are going to be very difficult. Why? Because it has multiple branches and there are no constraint here, right? Like any parent can have any number of child nodes here. If so, the tree size would become huge and the number of branches also would be higher. Since the branches are higher, to perform the operations when it comes to the traversal, or if you want to perform any searching operation, since it has wide number of branches here, it is going to consume much time to perform the searching operation, because it has to visit many number of nodes at each level here. So it is going to be very complex, and the time complexity which it is going to take to perform any operation in a general tree is going to be higher. So it is not, the general tree is not going to be the preferable tree structure to use it in any of the application, in most of the applications. And the second type is going to be the forest tree. Forest tree is nothing but it is a disjoint union of trees. A set of disjoint trees or forest is obtained by deleting the root node. If you delete the root node here, for example, if you take this general tree example, if I delete the root node, this root node would get deleted. Since I have deleted the root node, all these edges also would be disconnected. Since the deletion of root node has been done, all these subtree would act as a different tree now, since there is no root node to connect, right? So all these would become a separate. So each and every of this we call it as a forest here. So the forest can be enabled by deleting a root node in a general tree. If you check here, there is no root node here, or each and every subtree, each and every tree is acting as a forest here, the different tree, and all these can be combined by introducing one root node here in the forest. So a forest can also be defined as an ordered set of 0 or more general trees. So if you check here, 0 or more general tree, we can call it as a forest. Since by definition we defined it is a set, the set also can be empty, which means a forest can be empty also, or else it can have more general trees. So 0 or more general tree can be combined, which would form a forest here with the help of the root node. So all these are a general tree. This is one general tree, and this is number 2 general tree, and this is number 3 general tree. So each and every general tree would act as a forest. By combining all, you can create one main tree also here by introducing a root node. This is what the forest tree is. We can convert a forest into a tree by adding a single node as a root node of a tree. So here I have introduced one single node, which is a root node. By introducing a root node, I have combined all these forests. Yes, I have combined all these forests and created one complete tree. So by combining the forest, we can convert a forest into a tree by adding a single node. This is what the forest tree is. And the next type is a binary tree. Binary tree is again a tree data structure in which each node can have 0, 1 or 2 children, which means if there are 2 children, one child is going to act as a left child and another child is going to act as a right child. So at most 2 children the binary tree can have, which means it can have any parent. If you take, it can have, for example, parent 1 is there, it can have 0 child node also, otherwise it can have only one child node, otherwise it can have two child nodes also, but not more than two child node it can have. That is why we call it as a binary tree. Binary means 2, right? So, it can have at most 2 child nodes, either 0 or 1 or 2 it can have. That is the main constraint in binary tree. Why? Because only if we restrict the child node, performing operations is going to be much easier. If you do not restrict the child node, the trees will go wider, and when it comes to the searching operation, it is going to be very difficult. So, the maximum number of nodes at any level in a binary tree is going to be 2, not more than 2 at any level if you take. So, this is a root node, we can ignore this level, but if you take this level, yes, at this level each node, if you take the root node A, it has only 2 child nodes only. If you take this level, if you take the next level, the root node D is there, sorry, the parent node D is there, since it is acting as a root node, by acting as a leaf node. Why? Because there is no child node. So, it is a leaf node, and if you check this as a parent, it has 0 child node, right, which falls under the category of binary tree only. If you take node E, it has only one child node, which is binary tree one, which is satisfying the binary tree constraint. And if you take the node F, it is acting as a leaf node. Why? Because it does not have any child node, which means it has 0 child node. So, it can have 0 child node, 1 or 2 child node, but not more than 2 child nodes it can have, which means maximum 2 child nodes a binary tree can have. And next type is binary search tree. When it comes to binary search tree, it is also called an ordered or sorted binary tree, in which the value at the left subtree is lesser than that of the root node, and the value at the right subtree must have greater than that of the root node. If you check here, it is a variant of binary tree only. The only difference is, while storing the data elements, you must ensure that all the elements which are coming lesser than the root node should fall under the left subtree, and all the elements which are coming greater than the root node should fall under the right subtree. This is our left subtree of the root node, and this is the right subtree of the root node. If you check all other elements, like in the left subtree, all these are falling lesser than the root node 30. And if you check all the data elements in the right subtree, all the elements are greater than the root node. So, the binary subtree will have the elements which are coming lesser than the root node in the left subtree and greater than the root node in the right subtree. That is the constraint in the binary search tree, which makes the searching operation more efficient here. Why? Because there is a constraint here. Always if you want to search one particular element, for example, I want to search 10. So, first always, since the root node is the origin of the tree, first we need to compare with the root node. If I compare with the root node, it is coming lesser than the root node, 10 is coming lesser than the root node, which means since we are following the constraint here in the binary search tree, the number which is coming lesser than the root node should fall definitely in the left subtree, right. Since it is coming lesser than the root node, definitely it will look into the left subtree and it would completely ignore the right subtree. So, the time it consumes the time to traverse the data elements while performing the search operation is going to get reduced over here. Why? Because since it is coming lesser than the root node, it can completely ignore traversing the right subtree. Why? Because all the data elements which are there in the right subtree would be having the values greater than the root node, right. We need only we want to perform searching the data element only 10, right, which means it would fall definitely in the left subtree. We can completely ignore this, through which we can save the time by avoid traversing the unnecessary data element, which is not going to satisfy the constraint. Then again, this would be compared with the next level, the next root node. It would compare again whether 10 is lesser than 20. Yes, since it is lesser than 20, definitely in the left subtree only it would be. Then again it will come here, it will check here, it will compare the element which it want to search along with the root node, but since it is equal, which means the element is found. So, if you check everywhere, if you check 30, the left node 30 is the left child node of 30 is 20, which is coming lesser than the parent node, and if you check 50, the right child which is greater than the root node, which is 30, and then again 20 is acting as a parent. The element which are coming lesser than 20 should fall in the left hand side, and the element which is coming greater than the 20 should fall in the right hand side. So, always the lesser element should fall in the left hand side and the greater element that the parent should fall in the right hand side. It follows this constraints. So, this would make performing all other operations like traversing, insertion, deletion is going to be more efficient. And the next type is expression tree. Expression tree is generally used to store algebraic expression. Again, this is the variant of binary tree only. To store the expressions, this binary tree structure can be used, which is called the expression tree. For example, let's take the sample expression a plus b star c plus d, and this expression can be stored in a binary tree structure. If you take a plus b, so if you check here a and b, all the leaf nodes, if you check, it would be an operand, and all other intermediate nodes and root node will be holding the operators here. Let's discuss this expression tree in detail in upcoming video with a few more examples. You will understand it in a better way. And this is the sample expression, and this expression has been stored in a binary tree structure. Since we used this binary tree structure to store the expression, we can call it as expression tree. And the next type is AVL tree. AVL trees are the special kind of self-balancing binary search tree, where the height of every node's left and right subtree differs by at most 1. If you check here, the height of this left subtree is going to be, the height is nothing but the number of edges in a tree, right? The height of this left subtree is 2, and height of the right subtree is also 2. Now, suppose I am adding one more data element here. Okay, I'll add it here since it is 10. Okay, I'm adding one more data element here, and without violating the constraint, we are supposed to insert it without violating the constraint of binary search tree, because it is a variant of it's a special kind of binary search tree, not binary tree. In binary tree, we can store element in any order, but at most only 2 child nodes it should have. But when it comes to binary search tree, it follows the same rule of binary tree, which means at most 2 child nodes only it can have. But the thing is, when you place an element, you must ensure that the left child node is having the value lesser than the parent node, and the right child node should have the value greater than the parent node. So if I check here, it has 11, which is acting as a right child node for the parent node 10, which is coming greater than that only. And also if you compare it with the root node, the 11 is coming lesser than 12 only. So it is falling in the left subtree only. Without violating the constraint, I have included the new node, which is 11. In the upcoming video, we will discuss in detail how to perform insertion and deletion in a binary search tree without violating the conditions. For example, for instance, I am adding one more data element 11 here. Now if you check the height of the left subtree, which is 3, right? And if I check the height of the right subtree, it is 2. So according to the condition, if you check here, it is a self-balancing binary tree, and the height of every node's left and right subtree differ by at most 1, not more than 1. If it differs more than 1, it would not be balanced. So mainly this AVL tree structure, AVL tree technique is used to balance the binary search tree. Why? Because if you take okay, let's generate one more binary tree, binary search tree. For example, the root node has 30. Now I want to insert 20. Since 20 is coming lesser than 30, it should act as a left child node for node 30. Then again I want to insert 10, which is coming lesser than that. So this is acting as a left node for the parent node 20, and then again 5 I want to insert. Since it is coming lesser than the root node, it should fall in the left subtree. According to the constraint, this is the right place to insert 5, right? So if you check here, this is also the binary search tree only. The main use of using this binary search tree is to save the time, to reduce the time complexity, to perform the operations like searching in a more efficient way. We use the binary search tree, right? So if you check here, this is binary search tree, but if you check, it looks like left skewed tree. We can generate it in a more efficient way, in a more balanced way with a lesser number of 8 also. But since we followed strictly the binary search tree, it follows the skewed tree. It appears like a left skewed tree. So the total complexity is going to be the height only. If the height is 3, it means that the number of iterations which it is going to take to perform searching operation is also going to be 3, right? So we can generate it in a more efficient way also. Instead of the root node 30 is the data element 30 is acting as a root node, we can make 20 act as a root node, and we can regenerate the tree, we can reconstruct the tree in a more efficient way like this also. If you check now, the height is going to be only 2. Now we can call this as a balanced tree, and also we can call this as a avial tree also, because if you check the left subtree the height is 2, and if you check the right subtree the height is 1. As we said here, the height of every node's left and right subtree differs by almost 1. Yes, it differs by only 1 only. So the main use of using this avial tree structure is to generate the balanced tree structure. We are using it when we face the worst case scenario in a binary search tree, especially if we get a skewed tree, we can reconstruct the tree in a more balanced way with the help of avial tree conditions. So the main use of avial tree is to construct a strictly balanced tree. We can go with this avial tree. And the next type is a B tree. B tree is again a self-balancing search tree wherein each node can contain more than one key and more than 2 children it can have, each node can have. So each node can have one key and more than 2 children. So it is a special type of, we can also call it as, it is a special type of M-way tree. And while discussing B tree, you will be more clear. And B tree can store multiple keys in a single node, and also it can have multiple child nodes. So if you take any node, it can store a multiple key and it can have multiple child nodes also. The main purpose of using this B tree is to reduce the height and to enable the faster disk access. The B tree structure can be used. The applications of B trees are in databases, this can be used, and for the file systems this can be used for multi-level indexing, and if you want to perform quick access to any data stored on the disk, this can be used. And these are the applications. And yeah, in this video we discussed a few types of tree structure, and in the upcoming videos all these types would be discussed in detail with examples and its properties. Thank you.